Hello everyone, we're Team Fastfold AI. In the last few years, we have seen many foundational models or breakthroughs like AlphaFold, RF diffusion, or even bolts. Both gens recently allow scientists to design binders towards small molecules, protein, or antibody. However, there are some remaining key challenges in this space, like data scarcity, especially in antibody antigen domain, designing the selective binders towards one target but not the others. Or even the problem that is pronounced in adaptive bio sub-challenge is to design the binder towards difficult target to test in a wet lab for FCGR3 and 4. During this hackathon, we are building the platform that addresses these challenges through a multi-target optimization framework. Through this platform, it provides intuitive, easy-to-use user experiences for protein designers to translate scientific intuition to actual final design molecules through just drag and drop and a few clicks. So in this hackathon, there are two main use cases that mostly benefit from this framework, which is to design selective target. That is very important for the binders that like causes off-target binding risk, or design the binders towards dual targets that addresses the adaptive bio sub-challenge, which is relevant for observing proxy effect through the easier target to test in the wet lab.
Hi, my name is Hari Prakash. Non-selectivity in GPCRs is a big problem. So GPCRs are signaling proteins, and one of the proteins that we focus on for this hackathon. So delivery of non-selective GPCR drugs can end up switching on completely unintended receptor subtypes and end up having serious side effects. A great example of this was the anti-obesity drug in the 90s, fen-phen, which was withdrawn after it ended up activating receptors on the heart valves, which ended up leading to heart disease, hypertension, and also ended up generating $13 billion in legal costs and settlements. It's thus really important to design selective binders to avoid such issues.
The workflow for designing binders that consider multiple targets is still quite fragmented and misses some key elements. Current solutions like bolts-gen still face several challenges. First, the design specifications often require manual adjustments in the YAML files. Also, there is no explicit support for handling multiple targets simultaneously. And running the pipeline isn't automated on a user-friendly platform, making it harder for non-experts to use. We developed two pipelines. Our first three-stage pipeline identifies selective binders. Stage 1, generation, uses bolts-gen to create M candidates optimized for a positive target. Stage 2, screening, filters for the top N candidates and uses bolts2 to predict their cross-reactivity against K negative targets. Finally, stage 3, ranking, calculates a selectivity composite score, which is a weighted sum balancing on target affinity, a PTM, prediction confidence, PAE, and interface plausibility, delta SASA. This composite score is then used in a Pareto optimization analysis to visualize trade-offs and select the best candidate. For dual target design strategy, we leverage the existing binder and human receptor FCGR3 from available PDB. For targets, though structure is unknown, in our case, it's FCGR4, we predict their structure using bolts2. Then we identify the common hydrophilic target, a region between two targets. And after that, we obtain the protein interface score out of multimer predictions and rank the design's candidates. And now Julio, my teammate, will give a demo of our platform.
Hello, this is Julio here. Let me show you a demo of the platform that we built for this hackathon. So here I will start using the workflows. This is a standard bolts-gen. So very visually, we're using React Flow on the front end with React. So users can start defining inputs here. I load an example here. Also start very quickly checking what's going on. So I'm designing a binder on this region here. As you can see, different coloring. That's pretty nice. And I can also define different settings for the bolts-gen run itself. As you can see, different design, a budget that will impact compute on runtime. And I will show now, this is the binder optimization pipeline here. We also build a YAML specification on top of that. So you can define positive and negative binders. This is an automation that we did to do selectivity scoring for multi-objective. As you can see, you define the binders. And also we have post-processing steps here for selectivity scoring with multi-objective with different parameters. As you can see here, that's pretty nice. And we also have this very cool use case for multi-target. So this is dual target. I'm able to define binder scaffold from existing structure and an unknown structure from a target PDB. And I should be able to generate as a pre-processing step a specification for the bolts-gen run. So that is running. This automation is running on background to extract very specific hotspots using that structure defined there. As you can see, that's the result. That's pretty nice. And can also check what's going on here with the Molestar integration that we have here. Nice. And as you can see here, we also have post-processing steps for PPI interactions with bolts2. So this is using this target, and we're also ranking them at the end, having into account the IPTM scores. So let me just show you now. We also have job management. I will show this demo this is for a dual target. And as you can see, I have the rank 1 highlighted here, and I have the different metrics from IPTM and also for the original bolts run merged together. So I should be able to very quickly inspect the results and, make decisions about how to run it again, because this is an iterative problem. We don't think this is one shot. People should be able to do a lot of iteration with it, and if you have the data, you should be able to do it. And here you can also inspect all the results, PDF, zip files using the Molestar integration, and also you should be able to see CSV on data tables. Let me just quickly show you another example. I think I have this one, which is a 4-hour run. That's a lot. And you should be able to see also, for example, here, multiple plots from the post-processing steps for the selectivity scoring and affinity scoring. As you can see, very flexible indeed. I think that's what we wanted to build. And hopefully this will be very useful for users. We validated this with experts. They're liking it. And I think this is very powerful tool to build on top of that. This is public for use on evolved.fastfold.ai. Hope you like it. Thank you.